Now armed with our new compression model, the idea of self-extracting bits, let's talk about a specific input that we want to compress. So here on the left is shown a tree that I generated with the first Java program that I wrote in my modern life when I first started teaching, my first semester professionally teaching. So at Princeton, there was an assignment where we had to use recursion to generate art. And in this case, I did some random recursion and built what I thought were pretty cool looking trees. Now this is a file that is ultimately, it's an image, and images are just the sequences of bits. So in bitmap format, if you were to actually open up this file and look at the bits, you would see a sequences of ones and zeros. Now, in order to make the representation more compact on the slide, I have written it out in hexadecimal. And you may not have seen hexadecimal before, but 4-2, you can just think of that as some binary digits. Okay? So in other words, this tree here can be thought of as this stream of bits, 4-2, 4D, 7A, 00, 10, etc., for a total of about 8.4 million bits. Okay? So I can compress this by looking at chunks of data. For example, this right here is going to be a total of 8 bits. This is 8 bits, this 4-2. And I could treat that as my first symbol. The symbol 42, the symbol 4D, the symbol 7A, the symbol 00. Looking at this, what's the very common symbol? 00. What's another very common symbol? FF. And so those symbols are going to get relatively short code words. So I run my Huffman compression algorithm on this, and I get back two things. First, my decoding try, which when I did the experiment, ended up being around 2,560 bits. Okay? And in this case, the total number of possible code words that I had, of symbols, was everything between 00 and FF. Okay, so the total cost of the decoding try at the front of my file was 2,560. And then the compressed data after I use Huffman coding looks something like this. So it is also a sequence of bits, which now I have written in hexadecimal again, and that was about 2 million bits. And so in total, if I am honest with myself and I include the decoding try, the image data, and the code for Huffman.java itself, then I'm going to get 2,037,000, etc. bits, right? So it's important, according to Model 2, that we're going to package the code needed to decompress everything. The Java code needed to decompress everything. The decoding try needed to decompress the input data, and the input data here, the compressed version of the input data. So this is the compressed bit stream, around 2 million bits. And if I feed it to the Java interpreter, it's a self-extracting Java file in the sense that it will spit out the sequence of bits corresponding to HugPlant. That'll be about 8.4 million bits. So take the sequence of bits, give it to the Java interpreter, and you get 8.4 million bits. Okay? And so ultimately, if you think about this visually, we have a small version of the plant that is fed to an interpreter, and we get a larger version of the plant that we can now view in some, say, web browser or some photo viewing app. All right, so that's where we're going to stop for today, and we'll pick it up in the next lecture and think about the implications of this model, and it'll turn out to be pretty deep and interesting. So I hope you'll stick with me. I know it's pretty heavy-duty stuff, yeah, let me know if you find it confusing, and I will do my best to try and make it better. All right, see you next time, and yeah, good night.